So that is agenda for today, and we have shared the link to a YouTube video with last year's presentation, but I know you guys are all busy and it's a luxury to spend 1 hour to watch it. So we will have a short recap. After that, we will have a quick look at the official testing approach that OpenTelemetry framework proposed to engineers. We will discuss what is wrong with it and how we can make it better. And after that, I will make a short demo of OpenTelemetry testing library that born as a kind of trial of failures. So that is a battle-proofed approach for testing OpenTelemetry instrumentation code. So let's go to the first point. So what is OpenTelemetry? First of all, it's a standard and the framework. The framework is available in various languages, so we can say that it's a language agnostic, and the concepts are everywhere the same. And there is also a protocol. OpenTelemetry doesn't provide you any kind of backend solution for storing data and displaying it. You can use either open source products like Jaeger, Prometheus, Zipper, or you can use some third-party vendor log tools, because there are plenty of them. If you use OpenTelemetry for instrumenting your code, you have a luxury to later on switch between the tools. So that is a good benefit for instrumenting your code with this toolkit rather than with some proprietary stuff. So yeah, as mentioned here on the slide, OpenTelemetry covers 3 areas: traces, metrics, and logs. We will be focusing in this presentation solely on tracing and testing of the instrumentation part. So what is a trace? Normally, a trace is a way how you can track what happens inside the system in response to some requests. So when you have a query, normally there is some root span created within the system and reported. And the root span normally has span ID and trace ID. So that is a way to identify spans. And also, root span doesn't have any parent ID. Within the root span, for some smaller activities, the system can generate some subspans, and those subspans will share the trace ID of the root span. They will have unique span ID, and they will have assigned parent span ID. So that is a way how you can later on build up the full picture, how those spans are nested and related one to each other. So we have introduced the term span. So what is a span? As I said, we identify spans using trace ID, span ID, and the parent span ID. But also, span must have a name. It can have some additional attributes. Normally, those are key value pairs. It can have some links to other spans that have some other trace ID. So by this, you can create a relationship between multiple traces. It can have a status. Well, it does have status, but if you doesn't change it by default, it treats it as a successful execution. But you can set it to error. And there are events that can be spawned within a span, and they will be attached to a span. So that is a way how normally you can display spans in a Jaeger. So that is one of the most popular open source tools. So what we see here, I'm not sure, I hope it's visible, but yeah. Well, on my display it's much better. Sorry guys. But here on top, this bar, it shows the length of the whole root span, and this smaller one, it's it's our nested span, or child span. So you can see that root span status is an error. So here we have an attribute, and there is a reference which, well, it's named reference in the Jaeger, but it's technically a link to another span with another trace. So there is a span ID of that link. And here for the nested span, there is a event. It's showed here as a small bar. I don't know, it's visible, no? Yeah. Because spans, they do have start time and end time, so that is some processing, while event is something that shuts immediately. So like it happened, and you can treat it as a kind of logs on steroids. Every link and every event can also have attributes associated with it. So when you have event, you can attach some data, and here's a event attribute on the bottom. So that's how it looks, and that's how it's generated. So we have a very straightforward code. You can see the nesting, it's visible from the code. So we have a root span, here is a name, here is a link. So that is a creation of the linked span and extraction of the context. Setting some attributes within the span. And here's internally, as long as you run within the context of one process, you don't need to worry about the context propagation. So when you start another span within your like parent span, the nesting will appear automatically. Because normally OpenTelemetry framework stores data in process dictionary, so it picks up the existing span ID before creating a new span, and sets it as a parent. And yeah, here is an event that we discussed on the previous slide. Yeah, and that's mostly it. The code looks nice as long as it's on one page, but normally it's not so. And the official way how framework recommends you to test your reporting is switching to a simple processor in a configuration. So that's important for us because normally spans are reported as batches, and you need to wait for the batch to collect before you can process it. A simple processor ensures that everything that fires right away, and there are no delays for it. And also, there is a SYN. It is a part of an OpenTelemetry standard. So when it's called exporter in technically every framework for every language. So that is a term from a standard. So exporters normally support various standards that you can use, because you can have OpenTelemetry standard communicating to some external backend, but you can also use some exporters that implement native standards for third-party solutions. And this exact exporter, it's called exporter PID, it, instead of sending somewhere data, it just create a message and send it to some process within the system. And what framework recommends you to do, to set your test case process as a receiver, receive all of that spans, and later on manually analyze them. So I probably will switch now to a page because the testing page is very short. That's technically it. Here they have data about the configuration you need to provide in order to intercept the spans. And here is an example that actually just asserts that some span raised and nothing else. But it's just not enough for testing. We normally would want to test that spans are containing required attributes for us. We want to test that the nesting is done properly, and all of that aspects, it's proposed to you to analyze them manually. I tried it, but on a third microservice that I had to instrument and test, I understood that it's not the real way to go. It's just not working. Because at least 2/3 of your test code would be just parsing of that spans and checking the data. Also, additional problem is that the message that you intercept, it contains Erlang record. And just to make things even more funny, the record is not the end scene. So like it contains some fields that are also records, and some of that records are module internal. So in Erlang code, you cannot get a definition of that record in an easy way. So I would say that it's not only a headache for Elixir programmers, it's also a headache for Erlang programmers as well. Yeah, so, yeah.
Make it full screen.
Yeah, sorry. So the record, sorry, I have a personal touch with this records. The record is one problem, but what else can you guys spot as an issue with this approach?
Spots are coming without correlation to each other. You have to correlate them manually. If you want to know, you go to the default hierarchy. So not only you have to parse them, you also have to organize them into a tree to make a meaningful data for it to be analyzed.
Yeah, well, you can obviously analyze the relationship between parents. So like you can extract the span ID of the root and then check that expected children have it set as a parent ID. So yeah, that's another issue.
Order is an issue.
Yes.
Different processes.
But yeah, normally you would probably expect it by framework creators to collect all of the spans before you start processing them. So from one perspective, yes, you need to take care of the order by yourself. From another, you still grab first everything and then analyze it.
So first of all, how do you know you got everything? Like, do you hide code, receive 20 spans, and then you start processing? I saw that you can assert DC, which means that we cannot wait for everything to come in or something.
When?
The second thing I noticed is that the posting process that seems to be configured more or less globally, I assume. So then asynchronous testing is out of the window.
Yeah, it's absolutely correct that you cannot run tests in parallel because you set your test case process as a receiver. So technically, everything else, even if it's not testing spans, but results in the generation of a span, will hit you, and you will just have too much data to analyze, so you would have to manually extract it, or you're just giving up on parallel execution. And regarding the asynchronous collection of the spans, unfortunately, I would say that it's a normal issue. Like we have to deal with it. So like even if you have, for example, in some mocks, and you expect somewhere asynchronously something to be triggered, you're just waiting for that to be triggered, and well, waiting for some time and then giving up. So I would say that it's just the same issue here. Yeah, you just need to think about it as a delay you need to have in a test case. And actually, if you introduce that delay in each and every test case and you run them in a non-parallel mode, it results in a huge execution time. And that's another headache. When you just do some extra testing and suddenly your CI pipeline starts to run for 5 minutes instead of 20 seconds. So yeah, we named it all. And one of the things why records are bad when you test them. So even if you use Erlang and syntactically it looks nice, you still, in a crash report of assertion, have tuples. And that is very big structure. Trust me, it is really very ambiguous structure of 20 fields, and some of the fields are actually another records of 5 or 10 fields, and it's just unreadable, absolutely unreadable. So one of the first things I did, I created converter from records to maps. And as I said, surprisingly, I did it for the Elixir project first. Erlang was done much later, first Erlang instrumentation, and surprisingly, Elixir allows you to do it in a simple way, since the record module, it provides you some macros that are running in a pre-processing time, and they analyze Erlang code and extract record definitions from Erlang code, and a record module doesn't care if it's a header or a source file, so you can technically analyze source files. You just need to provide where it's stored, the path to the file. So I hope the naming will not change from version to version, but still, if it changes, you're just failing to compile stuff, because, well, there is no more file for analyze. And you can just use this internal module records, because you analyze the code. For Erlang, you have to analyze the bin file and extract the stuff from debug info to have that record definitions. And well, that was an interesting task for me to do. The next thing is what you said. It's much easier to first organize things in a tree-like structure, and later on just a pattern match tree, so you don't have to manually parse span IDs and trace IDs of every span you receive, and that can be a generic code, so you can reuse it from test case to test case. It is a generic approach, and the tree itself, when you just pattern match against it, it looks much more compact and readable, so you technically can have all the attributes you are expecting in that pattern. You can have the tree structure that represents nesting, and you just check everything in one shot, and if something goes run, you're normally, well, at least in Elixir, it nicely highlight you what doesn't match. But the pattern is a nice approach, but it has issues as well. So the first issue is that you need to know a position in a list. And actually, in asynchronous system, you kind of don't. You cannot be sure that asynchronous spans are arriving in one and the same way. And you either need to first sort that stuff, which kind of defeat the purpose, because you need to additionally preprocess your tree structure, so each and every list is sorted. And even in this case, if someone is, for example, adding some additional attribute, and attributes are represented as a list, so it can inject somewhere in the middle. So technically, in your logic, you're testing some attributes. They are still there, but there is something in the middle, and the match fails. So you need to do some more moves and adjust your test code each and every time you change some implementation aspects. So the second thing is that imagine a situation that, for example, you have two test cases. And in one test case, one of the spans should fire an event, in another it shouldn't. So normally, you have one and the same span tree, but for one test case, you need to check that event, in another, you don't. And there is no possibility for you to construct conditionally pattern, because that is not a data. If you want to match just some of the aspects, so like not a full match of the structure for equality, you need to have that written down in code as a pattern, and those patterns can be like 15, 20 lines of code, and your size of your test case just grows exponentially. And well, after implementing it, I understood that it looks nicer now, but I still need something better. And the better way is to have just private pattern matching logic. So that is a function that accepts data. The first data is your pattern, so you can build it. And the second data is your tree structure. And there is a logic behind that allows you to check, verify the tree against the pattern. And in this case, you can also overcome the list problem, because you can just say that there must be something that matches the item in the pattern, but it doesn't need to be in some exact position. So yeah, and the last thing, parallel execution, because again, when for just small additional testing of the spans, you're like tripling, quadrupling, and etc. execution of your CI pipeline, it looks bad. But in most cases, if you just wrap your scenario in some dummy root span, you can just collect all the spans somewhere globally, and then extract all the nested spans using trace and span ID and build up the tree. So you can just run things in parallel. You don't care how much stuff is collected in some collector. You know the way how to extract what's important for you in this test case, because your test case creates a unique trace ID which is shared for all of the children's spans. And in the cases when your code is generating the root span, so for example, there is some cron job, and you cannot nest that root span within your test case, you can just switch back to non-parallel execution. You can just drop everything collected before, and then you know that everything generated during your test case is related to the test case. So you normally just use the name of the pattern for looking for this span and trace ID of the root span, and continue with a normal approach. So the good thing that everything mentioned before, I made this pass. There was long trial. I failed multiple times, but apparently the solution that is released on GitHub, it's working. And I invested in testing quite a lot. I believe testing code is just twice bigger than the implementation, or maybe more. There is extensive prop testing there as well. So I don't trust myself in creation of the test data. I just created tons of prop tests. And yeah, let's have some demo. So is it readable, or should I make it? No. So what we have here, that's technically what you're expected to place in your config X. So we're setting exporter to none. So it's not failing on a startup, because X unit starts all the applications related and dependencies before running test case. And we don't want any exporter to be configured on the startup. We set a simple processor with dummy configuration. And that is the OpenTelemetry library that I'm presenting now. So here is a code that we want to test. It is pretty similar to the one we saw on the slide. So what we have here, so it is a synchronous task. There is no span context propagation to it. So it is not this exact span, linked span, it's not appearing within our tree, but we are taking the span context, and we're using it as a link with some attribute for our main span. So on starting up, we're providing the links, and there is also a kind change to client. So we're setting some attributes. We're spawning a nested span with some additional attribute. And well, we're doing quite a few things to test, let's say. And yeah, that is a trick to run XUnit in a livebook. And that is something you're expected to run just once in a test helper. So you're starting the collector code, and it's generally a gen server with add stable, and it just stores every span it receives in add stable, so it can be later on processed in parallel, because we have a parallel reading configured for table. And you just run it once. And for the case when you want to fall back to a non-parallel execution, just to avoid searching through all of the stuff generated before that non-parallel switch happened, you can just run OpenTelemetry testing reset, which will remove all the stuff in add stable. So this is absolutely fine, because when you run in a synchronous mode XUnit, you have a warranty that none other test cases are executing at the moment. So you just do it within test case. Okay, so here is a wrapping in some dummy root span. So we have scenario, and we just wrapped execution and in the end we're getting span IDs. Normally they are in a record, Erlang record, so OpenTelemetry testing provides you a nice helper to avoid that record parsing. And having that trace and span ID, we wait for the span to be reported, because collector is an asynchronous process. It may need some extra time to store everything in ads, because, like, well, messages are processed asynchronously, and that is normally the way how you do it. In our exact case, all of the nested spans are done in the context of the same process as the main span. So we know that we don't need to introduce any other delay in a test case. So once the root span is reported, we have a warranty that everything else is reported as well. And we're fetching a tree-like structure from the collector. So, well, it actually builds that tree, which looks like a tuple of two elements. So the first element is a map, a representation of a span, and the second element is a list of child span trees, because, like, each child can also have its own children, and it is a recursive structure. So we can take a look later on, because I added inspect for the span tree, and here is a pattern. So as you can see, to test everything we've added in that demo scenario and use auto formatting, it consumes how many? 30 lines, more than actually the code that produces it. But we are testing here everything. So, like, we have a dummy root span, and we don't care about any other fields. So we want to test just the name. We have the main span. We have attributes expected to be there. We have a status code error because we said it, and the kind we changed to client, and there are some events inside. The event has attribute as well. So the link is added with attribute, and it's already here. Here is a nice thing. So it actually works pretty similar to a match spec for add stable. So when you use some atoms that starts with a $sign, it actually doesn't check for equality. It matches anything, but in the end, you will get a map returned with the keys with the keys equal to this special atoms, and the values is actually what's in a span tree under this field. So you have a meaning to extract some data by pattern matching as well. And there is also a nested span. So we use a bank version of a match function. So it does matching, and if matching is successful, it returns you a map. So here is that map with link trace ID and link span ID. So we're using that values. And now we can build the span tree for that linked span and verify it as well. So that's the name, and we added some attribute to that span. And we're also matching. So that's actually it. Let's try to run it, and let's see how it looks, how the span tree looks like. Oh, sorry, it's not actually execution of the test. So yeah, the test is successful, and let's go to the top and check how the span tree looks like. So that's the tuple. The first element is a map, and it's our dummy root span that we used. Well, it contains obviously a lot of fields, but we don't care about most of them. And then there is a list of children trees. So here we have a main span. And unfortunately, when you print a map, you cannot arrange a keys in the way you want. So, but it's a main span, and the attributes are there. The link added, it's here. You have span ID, trace ID. So that is actually the data that we extract using the special atoms. And yeah, and that span also has a child span. And here it is. It is nested span. So let's try to break something. I don't know, let's say like this. And reevaluate. So now we see that there is a failure. The failure at line 83. So that is line 83, where the match is happening. And here you have a report of from that matching logic. It explains in details what exactly has failed. The output is pretty ambiguous, and one of the reasons why it is so is because when you the custom logic for matching the list is that you're technically taking one by one elements from the pattern list and try to find the matching element in data list. And every time you have a match, you're taking out from a data list the matched element and continue process. But at some point, when the match fails for the list, you technically need to ensure that for some exact pattern, every item in the data list fails, and it reports also how every data in the data list failed. So you have like a test result for each and every item in a data list here as well reported. So yeah, that's actually it. And we have some probably time for questions, do we?
Yeah, fine.
No questions? Oh, okay, go one by one. I don't know.
If the tests are not executed in the same time in parallel, what compels it to make nested spans instead of one big span?
Well, first of all, what span is for. So you can measure the time, execution time of some subtask. You can have a clear split of the data. So for example, instead of reporting everything as attributes for one big span, you know that that exact attribute is related to this chunk of work. So yeah, obviously you can just go with one span, but it defeats the purpose.
So the span itself have only start time and end time. Doesn't have the start and end of every instruction in it.
It has start time, end time. It has how it works in the framework when reporting is started for the span. So like that underneath this with span, there are functions like start time, and it creates a record in some edge table, and then collects all the data associated with that span. So like you set attribute, it collects it there. You fire an event during that span processing, it collects it there. And later on, when you run end span function, everything that is collected, it is sent to exporter, well, or batched by processor, but later on anyway, sent to exporter as one chunk of data.
So I have to choose between doing it in parallel and having only information regarding this time span. If I want to look at what close.
No, as I said, normally you can execute like most of your test cases in parallel. And that there is no real limitation for this. You just need to maybe add this 2 lines of code for just having well-defined and well-known trace IDs that you need to analyze.
First of all, thanks for the presentation. It was interesting. My question is more like generic on how do you structure scans inside of this trace? I mean, usually we follow the code step, yeah. And how will you test them? Because when I think about testing code step, you can change the like in time, right? What's your experience in like dividing the whole like execution tree to different spans, and how you do it in production?
So that I believe it's just to clarify, it's not about the testing itself, but rather the recommendation for splitting the stuff. So the official recommendation is like that. So you don't want to have too many spans. But if you have some reasonable chunk of work that is kind of can be separated, then it is good idea to split it in a separate span. So normally, in a microservice architecture, you would have each and every pass through from one service to another represented as a span, and within that spans you probably can have some 1 or 2 child spans if you really need them, because like it depends on what request is doing. So so you don't want to introduce too many of them, but well, at the project that I worked on, we had a couple. So normally there were just 1 nesting or maybe 2 nestings.
So the general recommendation is to divide by business functions. Yeah. So for example, like one microservice is one span. Yeah.
Look, there is a thing called sampling, and it is a bit hard to sample the data that is represented by like 100 of spans. So like you don't want a situation when you're just cutting off some spans in the middle and having some parent spans reported, because when you analyze such data, it looks to you like in the middle something doesn't happen, like that there is no processing for it. So in order to have that sampling reasonable, you would want to limit amount of nesting and limit amount of stuff you need to collect before you actually do a judgment whether it's the thing to store or not. But yeah, regarding the sampling, it's probably a separate topic for the next presentation, because it's a hard one. Like it can be done wrong, and then you kind of have a data, but it's senseless. Any other questions? No? Okay. Then I just want to say a big thank you to Nelson for helping me with doing the language check and helping with the documentation, because I'm currently in the middle of the documentation creation for that library. And Nelson is doing an amazing job on the reviews. Thank you.